All right, we're ready to go. Nice. Okay, so we'll be presenting about how to build an NV diamond quantum computer with optical tweezers. So we're going to take apart what exactly that means, bit by bit. But fundamentally, as most of you who are interested in quantum know, we haven't really settled on what the transistor for quantum is going to be. We haven't really settled on what the best thing it is to build a quantum computer out of. Some of you might know that normal computers had a lot of different approaches, like vacuum tubes and whatnot, um, and biological bit representations that technically competed until semiconductors just emerged supreme. And these centers in diamonds are one of the most interesting platforms for computing. Personally, I would say they're the most interesting for quantum sensing, but they have been put forth as an architecture for quantum computation, and we're going to show you how exactly that works and why there's good reasons to be excited about this, especially because I feel like in the last few years it has been getting less attention, so it's a good piece of background to have in your arsenal. We're going to start, however, with I think you can go to the next slide. We're going to start, however, with optical levitation. So we're going to start with how optical tweezers work. These are very important tools, not just for NV centers and for um, yeah, I can't simultaneously monitor the chat. So if there's a question, please just feel free to interrupt me. This is an informal meeting. We're all friends here, so please just interrupt. We're going to first jump into optical levitation, which is an important tool also for other more established platforms such as neutral atom quantum computing. And then how an NV center works, and we're going to do an example on how to control it. And then Cody will explain to you the experimental details and highlight this from the perspective of someone who doesn't want to kill themselves as soon as they walk into a lab, such as myself. So optical tweezers are on the next slide. Nice. Optical tweezers are one of the most important, if not the most important tool that we have in, I would say, many realms of optical technology nowadays. Actually, the Nobel Prize in 2018 went to this very development of optical tweezers. The idea is based on the fact that light actually exerts a pressure. Photons carry momentum, as most of you who have taken some elementary physics might know. Therefore, when you place an object into a beam of light, it can experience a force. Optical tweezers serve to stabilize a particle in a specific position in space by applying these forces in an intelligent way. So you're going to have a laser field that is inhomogeneous over the breadth of the laser beam, done in a smart way. There's going to be two forces that act on the particle, the gradient force and the scattering force. One, the scattering force from simply photons being scattered by that particle, which acts as is drawn in the diagram, and then the gradient force, which is exerted by the inhomogeneity of the laser field. And they work together to find equilibrium in one specific spot that you're able to control. So when you place the particle just there, it actually remains in place, and you have a stable equilibrium. So that when you have some mild disturbance, it still stabilizes back to that spot. We're going to use this to levitate diamond particles, which are going to be useful for reasons we discuss later. But in theory, this can be used to levitate. I don't want to say anything because to levitate you would probably need a little bit of an overkill of a laser, but it can be used to levitate a lot of microscopic particles. Neutral atoms actually use the very same technology to levitate neutral atoms in place, to then perform quantum computations with that. So this is a core technology to understand, and it will be featured in any quantum electronics course you might take at university. Okay, now we're ready to move on to what NV centers are. So how do NV diamonds work? What do they do? Why does a quantum computer somehow come out of this? So NV diamonds sounds very fancy. You can go to the next slide. It's best to read that backwards. So what you have is a diamond, which is simply a carbon lattice. So on the right-hand side of this slide, you see that oversimplified. A carbon lattice is not square. It's a three-dimensional thing, but we're simplifying here. And NV stands for nitrogen and vacancy. So carbon atoms are number 6 in the periodic on the periodic table. Nitrogen is number 7, and so the nitrogen that you replace one carbon atom with carries an extra electron, and then right next to that nitrogen atom you have a V, which isn't actually a particle, that stands for vacancy. So that spot where there's something that's supposed to be there in the grid is empty. And now solid state physics can be a little bit complicated. And so you can look at what the electron orbitals look like when you have this arrangement, when you have a homogeneous diamond lattice, which you obviously find in nature, and then you introduce that single defect. And well, the quantum chemistry can get complicated, but the orbitals of the I believe it's 6 free electrons that are in touch with that vacancy, they form a specific pattern of possible quantum states. So in energy just below the state diagram that you would see here, you would have the conductance band, the valence band, and then just above you'd have the conductance band. And in between you get these discrete quantum states. And then in between the bottom and the top, you have metastable states. So the two just off to the side. Now, the two states that you see here at the bottom, these serve as your 0 and your 1 state. Depending on the M quantum number, the magnetic quantum number, you can have these are technically 2 quantum states that make up your 1 state, your slightly excited state. And then with M equals 0, that's your 0 basis state. And so there you go. Now you have a 2-level quantum system that makes for a qubit. And the reason the other states exist in this diagram is to read this out. So the way you would read this out is to excite the 0 and the 1 state with an additional laser. That is usually a green laser, just from how the numbers work out. You have that in the 500 something nanometer wavelength range, which is actually visible, which makes NV centers some of the most beautiful architectures for quantum computation, simply because all the light that you shine on it is actually visible to the naked eye, and then the diamond glows, and it's a very beautiful thing. And depending on whether it's in the 0 or the 1 state, you get a different decay process, leading to 1 state being dark when you point a camera at it, and 1 state being bright when you point a camera at it, which is ultimately what lets you read out the qubit. So move on to the next slide. Okay, but this is kind of what I have already explained. So with microwaves, you can I believe control the qubit, and then the emitted fluorescence that you can stimulate with that green laser allows you to read it out. And then APD is simply a camera, and you can look at the fluorescence, and whether or not it fluoresces tells you whether it's in the bright or the dark state. So it tells you whether it's in the 1 or the 0 state. So we're ready to move on to the very first protocol, which is to simultaneously excite a Rabi process and read out this qubit. So who here knows what a Rabi oscillation is? In one way or the other? Not all too many. Who doesn't know what a Rabi process is? One person. Okay, so one person for each, and the entire rest of the team is asleep. So that works. Rabi oscillations is a specific way to drive a system where making it go back and forth between the 0 and the 1 state, which I can represent as rotations on the qubit sphere. And something that is very beautiful that I think we don't include here in this presentation, but that I would like to encourage you to do, is to look up Rabi oscillation NV center on YouTube. And you can see how this Rabi oscillation is being driven, and then continuously the fluorescence is tested via this camera. And you can actually see the qubits sparkle like a star and turn on and off, proving that the process is actually working and that your control on the qubit is active, and that your qubit goes back and forth between the 1 and the 0 state. And you can literally see that turn on and off, obviously randomized as the readout process is random. But to see that kind of qubit sparkle is something that sadly we didn't have the time at the end to include in the presentation. Go to the next slide. So this is where we move into the experimental stuff. Cody, do you want to take it from here?
Sure, yeah. Let's go to the next slide. Basically, in order to do this experiment, you need microwaves to control the spin. And so basically this demonstrates like the different things that you need in order um to get the microwaves delivered to the diamond. Um, for example, you have different power supplies and voltage sources that hook up to a microwave amplifier, and that basically normally use something called a lock-in amplifier. So it's something that makes sure that it focuses like down the signal at a very specific frequency, and you use that to sweep the um, the signal to find out where you have resonance for your spins. Um, and then yeah, and then you of course you need a computer to control your arbitrary waveform generator, right? And what that does is basically it generates like an arbitrary like sine curve or flat top Gaussian some shape um at for the signal at a certain frequency. Um, and then yeah, and then there's also like a acoustic optimal modulator, and that basically um make sure like that makes sure that you get your signal at the correct frequency. And so what that basically is you can kind of think of it as like a local oscillator. So you mix the signal from the AWG, the arbitrary waveform generator, and the yeah AOM. And then yeah, and then also like when you read out the signal, right, it's from a laser. So the readout goes to a photodiode, and then it goes back to the computer. So yeah, next slide. So yeah, that's a picture of an example. So you have your green laser, and that's used for um the control, and then the red laser you can use for initialization. Um, yeah, so that's just taking out all the apparatus. Okay, next slide. Okay, is that it? Okay, I think that's all the slides then.
Um, all right. So before I open it up to like questions and final thoughts, I'd just like to say, so these were originally Oneka Singh's slides on NV diamonds. Unfortunately, due to business complications and like an emergency flight rescheduling, she was not able to join us today. Thank you so much to Cody and Alex for being able to take the spot and present this, and thank you so much QISCA and South Korea for bearing with us through all of this. Okay, we can open up the questions and final thoughts on NV Diamonds. I'll go ahead and share the screen again.
Okay, so I have a So thank you very much for your great presentation. So I have a question about with the NV Diamond's computational capabilities. So as far as I'm concerned, NV coupling two different qubits in NV diamonds up to a larger scale is very hard. Like, is that true? And if it's true, are there any like recent like breakthroughs in those research that can maybe couple NV diamonds with large number of qubits?
Um, sorry. Coupling NV centers is indeed difficult because basically you're dealing with magnetic dipoles, and the distance scaling is I believe was it 1/r². And so you get like a penalty for distance, and it's not so straightforward to bring these color centers close together. And so um I think with like optical tweezers, again, this is not my field, I might be explaining some stuff wrong, but I believe if you have like optical tweezers, you can move two particles close together, and that can allow some interaction. Some other ideas I've heard of is using a magnetic field gradient to kind of do like selective control on these different NV centers, because you'll get like different amounts of Zeeman splitting for your different states. I've also heard of like certain like deterministic placing of NV centers on wafers. I think I heard like a proposal about like DNA origami, because like NV centers, they're carbon, right? You can use some tricks from biology, right, to place like these certain um, was it enzymes or like something that allows like the carbon from the envy center to stick on to like a substrate, and you can place that in a way that where you can deterministically um, get the envy centers there. I think there's also like there's also like also like magnon interactions. I think I've heard like for a lot of these color centers, some people have been thinking about using like magnon interactions to mediate, but yeah, in my opinion, you probably don't want to use color centers to do quantum computation. Like these are very much more so for quantum memory and transduction, in my opinion. But yeah, or even quantum sensing. I think are the three major applications for color centers in diamond, silicon carbide, etc.
Okay, thank you for your answer. I have one quick question about optical tweezers. So I believe you're using diamond lenses for tweezing atoms with optical tweezers. Like, but if you would like to trap more than one atoms in a some kind of array or like a pattern, do you need multiple like lenses to trap all of those? If that's true, then maybe the scalability of the systems will be, I believe, greatly diminished. So is that true, or are there any other technologies that can trap uh, atoms, like array of atoms, by only using like only a few lenses?
Sure. So for this, there's actually a device called an acoustic optical deflector, and what that does is it takes your laser beam and it separates it out into like basically an array of laser beams, and through that you can scale up your optical tweezers. If you want like a reference, there's a guy who used to be a grad student at Harvard. Now he's a faculty at Caltech, Dolev Blovstein. If you read some of his papers on neutral atom quantum computation, you can like look at his like supplemental material. I think he includes it in his Nature papers. So if you look at his experimental setup, um, you can see that he uses optical deflectors to do a lot of his stuff. So yeah.
Okay, and what's the like the cause of the scattering forces there? So what's the IR? Is that the current or is that something else?
See, these aren't my slides.
Am I now audible?
Yeah, yeah.
Okay. So I think the I of R is the intensity within that laser field. So R is your movement, I believe, sideways, um, um, within the laser beam, and the scattering force is the force that the particle experiences simply because it scatters the photons, and then the gradient force is due to refraction. Um, and so obviously the force would be proportional to the intensity of the laser. The more intense the laser is, the more photons you're scattering per unit time, the greater the force is.
Yeah, and if you want to learn more about scaling optical tweezers and optical lattices and stuff, I would look at Dolev Bluffstein, Nature 2024, a logical quantum processor based on reconfigurable atom arrays. That's yeah.
Oh, and I have one question. This may be silly, but at the last video you showed us, the green laser just hangs the diamond particle in midair, right?
I think it shows that.
So my understanding of this animation is that the red laser is the tweezer, that the green laser is the a laser that stimulates the transition that is core to the functioning of the system. And then from the side, the thing that's pointed at the whole thing is the camera that checks for fluorescence. But again, like we didn't make those slides. I don't know where this comes from. So I would say this is a journal club. We're all equals here, and we can all try to figure out how things work. But that's how I would read um, the diagram. So you have the particle levitated in the middle, stabilized by the red laser, which is the tweezer. The green laser is the control, so to speak. It's the fluorescence inducing laser at 532 nanometers. And then from the side, you have the camera.
Why
And
do we
just to,
have to, yeah.
just to jump in here, Oneka earlier said it was an important point that the photo output was at the utter foci of this elliptical shape, so that the output would almost invariably reach there, given for some exceptions, since the entire interior was originally meant to be reflective.
Okay. What I don't get is why do we have to hang this diamond particle in midair? Why can't we just stick that to some surface or something?
That is definitely something that is also being done.
Yeah, you can also stick it to a surface. There's no harm in doing that. Yeah, I mean, maybe the idea. I mean, I didn't make these slides, but I guess like maybe if you do like an optical array or an optical tweezer, maybe the idea is to kind of use it as like a neutral atom type of idea. But yeah.
Okay, thank you.
Cody, would you expect that if the particle is smaller, the optical tweezer is the better way of suspending it, and if you have a larger crystal with only a single defect, that then fixing it physically to a solid object is more noise efficient? And that's kind of.
I
Do you
mean,
think that makes any sense?
I think if it's too large, you just can't use the optical tweezer to pick up your object, right?
I mean, okay, definitely, yeah. If it exceeds the capacity of the optical, um, solid reasoning. If it's too large, you just can't do it. But if it's small, the optical tweezer is always better because it provides a more stable and more controlled equilibrium. That would be my hypothesis, but not an experimentalist, so never listen to me.
So it's easier to make a small crystal than a large crystal with a single defect, right?
Actually, it's a little bit easier to make a large crystal with a single defect.
Oh,
So like for example, if I do ion implantation is the canonical way to do it in a larger crystal. So I can make an implantation mask, and then I can like poke a small hole in the implantation mask, right? And then only the ions get in, on that small hole. And basically like I know like that small hole, that area will have like single color centers. Another way to do it is like I have like a wafer of a bunch of color centers. I pattern a bunch of nano pillars, right? So I pattern a bunch of like small circles, and then I etch away everything outside of those small circles. And those are nano pillars. And then like those are like small enough so that you get like when you do your experiments, you get quantum emitters, where the photons coming from these quantum emitters or color centers, is the G square is below 1, which signifies you have single photons basically coming from, yeah. So like those are two examples of ways you can get it in bulk crystals.
Okay, thanks for sharing.
Yeah.
I have a question on. Oh,
Yes.
oh yeah. Okay. How do we implement like several qubit interactions? For example, like entanglements. How separate or like how close NV centers must be from each other?
I mean, it depends, I guess, on what you're trying to do. Um, I don't really do envy centers, so I honestly I don't know. All I know is I believe there's like a 1 by r cubed scaling in terms of the interaction strength. Um, yeah.
Yeah, that just goes beyond the scope of this presentation.
Okay.
Two qubit gates always require some kind of workaround that is usually native to the hardware. So with I think with superconducting, you actually leave the computational space and you match on the 2-0 state. And different architectures have different tricks that are native to the physics of the hardware. What
Yeah,
trick
but
that is for NV centers, I cannot tell you.
yeah, but for envy centers, what I can tell you is that the Hamiltonian, it's like a ZZ Hamiltonian. So your gate, so like if you have NV centers that are close together, you'll get a ZZ interaction by doing nothing, basically, right? By just having them close together. So, and then the strength of this interaction, how fast the ZZ gate goes, is kind of determined by how close the diamonds are together. Yeah, other than that, I don't know.
Thank you.
But you'd have to come up with some way of stimulating that, right? Because if it's just the distance, they're not movable within the crystal lattice. So they would continuously be, you wouldn't be able to control that. So there must be some stimulated control that you can apply to strengthen that in interaction. Just for the record. It probably involves lasers. All right. I think if there's no more questions, then we can thank everyone so much for their attention. And I'm very, very happy that we get to do this trans-Pacific Journal Club. And I think it's Korea's turn to impress.